Okay. Are there any questions related to that, what we were discussing last week? Today we will go on and mainly finalize. Maybe there's a short new topic after Christmas break, but the most of that, what we have to talk about is done after today. In January, we will have, I think, 2 sessions before the exam, and there we will finalize everything, and we will offer time for questions, Q&A. Therefore, all of you invite to have a look to the notes, to your individual notes, and that what we talked about after the Christmas break, so that you're prepared already. And if there is anything to be discussed, there's time to do that after Christmas. So this is now really a good chance to prepare, to have a look to everything. Of course, you should even recover and use time for your personal recovery, maybe for family, for friends, whatever. But hopefully there's a little time to have a look to chemistry related topics. Okay. Yeah, we are currently talking about metals, and we talked about steel last time. Here, just brief remembering the very last what we were talking about. Steel is pure iron, and pure iron, as we know, we won't find it as pure iron in nature. Mainly, it's an iron oxide. This is not noble. It's not a noble metal. It's an ignoble metal. So here, after a while, and in contact with oxygen, with other oxidizing molecules and compounds, iron is oxidized, and the oxidizing agent is reduced. So here we will find not iron, we find iron oxides. So as an example, we have the iron 2 oxide here. So iron 2 means the iron is the oxidation state +2, so the oxidation number is +2. And it's not that what we need when we like to have steel. We need the pure element. So without any oxidation, so oxidation number is 0. And therefore we have to reduce. For the reduction in the conventional industry today, mainly carbon. At the end, it's carbon what is new used for these reduction of the iron, and as an intermediate, we find carbon monoxide, which is doing the job at the end. And just looking to this reaction, we see here the carbon has +2. It's oxidized to carbon dioxide. Here we have the oxidation number +4. And the 2 electrons, which are spent from the carbon, when it turns to +4, it's taken by the iron 2+, and iron 2+ is reduced to elementary iron. To have the carbon monoxide, you have to go a step back to figure out where does it come from. And that comes from different reaction. The origin of these is pure carbon. We have the pure carbon, and it can be partially oxidized to produce carbon monoxide. That means we don't give too much oxygen to the system, so we won't burn it totally. When we burn it totally, it will be CO2, but then we need more oxygen. Giving only half of it, they say 1 carbon, half of O2, is 1 CO. 1 carbon and 1 O2 is CO2. That's total oxidation. What we see here is a partial oxidation. We don't turn it to +4 in one step, we turn it to +2. Partially oxidized carbon, and that's the carbon monoxide, which is needed for the reduction of the iron oxide. And there are in parallel other reactions, because of course we never can say there is really no CO2 in that process. So we will have CO2 as well when we add some oxygen, but at very high temperature and a lack of oxygen for total oxidation, we have additionally the Bourgeois balance. And the Bourgeois balance only happens when we have very high temperature, but that is the case in the steel production. We have more than 1000 degrees Celsius. And here, parallel to that, CO2 can react with carbon to produce more carbon monoxide. And this is an interesting reaction, because this C is oxidized to form CO, because it turns from 0 to +2. And in the same way, this carbon is reduced from CO2 to CO, because here we have +4 and here we have +2. So this carbon takes 2 electrons from the other one, and they meet in the middle. It's +2. That is the Bourgeois balance. That happens at high temperature, not normally, because when we normally have coal, it doesn't react with the CO2 in the atmosphere. We have a lot of CO2 in the atmosphere nowadays, 420 parts per million. It's much too much. And we have coal, but that normally doesn't react because we don't have 1000 degrees Celsius. Only at that very high temperature, it needs a lot of energy. Plus, so the enthalpy is positive, means endothermal. Only in this case, it can react to form CO, which is again needed for the reduction of the iron oxide. Okay, so here to interpret this reaction, it's very interesting. This is oxidized, this is reduced. Okay, fine. And there was a little homework for you. The question is, when we do that nowadays, we have CO2. At the end, we have carbon dioxide, and that is what we don't want to. Because this is the main greenhouse gas responsible for the greenhouse effect. Now, it was a big discussion last week in Dubai to say, okay, how can we stop the greenhouse effect? Now, we have to step out of fossil, of the use of fossil resources, totally. So even in the steel industry, we should not use carbon anymore. There is an alternative. We can use hydrogen. And the question was how hydrogen can be used to reduce the iron oxide. Any one of you thought about that? Please. Maybe you can come in front and use it. I'm not sure if those are online or able to see that. I'll try to manage it. 1 second. Camera control, maybe that helps. No, that doesn't help. Camera control. Camera.
But I think it's this sort of chemical equation.
One second, please. I just try to manage it that the students who are not here in class can see what you're writing. So online students, can you see it now?
Yes.
Yes, sir.
So the colleague in the class is writing the equation. I have to switch off maybe the other one. Okay. So yeah, now we did it. FeO and H2. You have a +2 here, and you turn to 0. That means you need 2 elements. Okay, so we have don't have +1 here. In the elementary hydrogen of the oxidation. Here. Okay, here we have 0, and it's turning to +1 2 times, and then 2 electrons are transferred and you have 1 more. Now one iron, one O, to H. That's it. Not difficult. So that's the big idea for future applications, not to use the carbon or the CO at the end, where CO2 is reduced. In future, the idea is to use hydrogen. But now the next question is, well, where should hydrogen come from? We already talked about it. What is the idea to create green hydrogen?
Electrolysis of water.
Electrolysis of water, exactly. Yeah, we split water into hydrogen and oxygen. So H2O is H2 plus O2, and we need 2 of them to balance it. But that needs a lot of energy. Here, energy is needed. The process is called electrolysis. And therefore, we need electrical power. Of course, green hydrogen only is green when the power comes from renewable energies. If you are producing hydrogen from fossils, well, it's not green hydrogen, because when you use a fossil like methane, you can create hydrogen out of methane, for example, but that's not renewable. Why? We call it steam reforming. With H2O, steam, so gaseous hydrogen, you can create hydrogen and CO2. Do you have an idea how to balance this reaction? Can you see?
Should be 2H2.
2H2O.
It will be 4H2.
4H2.
Yeah, now it's balanced.
Okay, check it. 4, 8, 8. Okay, 1C, 1C, 2O, 2O. Yeah, that's it. That's called steam reforming. Here we can use natural gas because the natural gas is mainly containing methane, 96%. That's the way how hydrogen is produced nowadays. More than 90% of the hydrogen production worldwide uses methane from natural gas. But that doesn't help because here you have carbon dioxide as one of the products. And therefore, this hydrogen can't be made as green. Because then we can use carbon and CO for the reduction of iron. There's no need to hydrogen coming from this way of production. The only way how it works is green hydrogen, via electrolysis using renewable power. Right? Because when the electrical power is produced via coal burning combustion, it's again CO2 at that point. So the only ways need green hydrogen. There are new future concepts now to say, well, maybe we can use the methane. It is not really green, but it's much better than these steam reforming. That's called steam reform. So it's steam reforming. But there's another idea, and in my research group, we are working on that, to use methane, but without having CO2 as one of the products, to use it for the hydrogen production. And the idea is, we call it methane pyrolysis. The methane pyrolysis is just split it in carbon plus 2 hydrogen via pyrolysis. And therefore, energy is needed. In any case, energy is needed. The idea here is we don't have CO2. We have pure carbon. And pure carbon, of course, we can store for millions of years. Pure carbon is needed in a lot of applications, like here we have black polymers. What's the color in there? It's carbon. We have tires, they are black. What's the color in there? It's carbon. And we have even quite some very high price carbon applications, like activated carbon. In the purification of drinking water, activated carbon is used very often. The activated carbon has a lot of small pores where the impurities are absorbed. So if you have a water which is not clean enough for drinking quality, you can filter it over activated carbon, and these impurities in the water are absorbed on the active carbon, and the water is clean for drinking applications. And that is used in quite a lot of different regions all over the world. High price product, and the form of the carbon fits to the application. Of course, it's not 100% green, but it is better to use methane this way to produce hydrogen instead of that way where we have CO2. The CO2 is emitted to the atmosphere again, and it's much more complicated to store it compared to pure carbon. So this is really field of interest, even in my research group, and maybe you join in when you are at the end of your bachelor program or internship or bachelor thesis, then you might be in contact with more details in that field. Okay. So if you are now able to deal with oxidation numbers, with oxidation, reduction, you are able to create or to read, to understand the different applications at the end, which are really relevant in future technologies. That's why chemistry is, as part in this program, important. The special program of engineering and energy systems and even industrial engineering. Okay. So then turn back to new topic. Yep. So one very important point is the corrosion of metals. Let's do these in an example talking about corrosion. Or well, let's start with what are you thinking? What is corrosion? The word, describe it with words. Oxidation of metals. Yes, in nature, when we have any kind of application, yeah, it could happen that the metals are not in the pure form like the iron, we have it, but when we put it out without any protection against corrosion, it starts to be oxidized again. And then we have the iron oxide, and you might have seen it, these brown, red particles falling down from the iron step by step, and at any time it's gone away. The stability, it gets in holes in some plates, whatever you have. So let's talk about the iron corrosion. And these are more steps. So in reality, outside this is quite complex. We have a so-called primary oxidation of iron. The oxidation, we always have, there is two parts in a redox reaction, the reduction and the oxidation. The oxidation is the iron elementary now is oxidized to form iron 2+. 2 electrons are delivered. And the reduction is here. Oxygen is available in the atmosphere, and in a humidic surrounding, we always have humidity in the atmosphere. Sometimes it's raining, then directly a drop of water is on our iron application outside. So in this environment, the oxidation of oxygen leads to hydroxide ions. Here we have the oxidation number 0. Here we have -2. So we have to add 2 times those. So we need 2 electrons per oxygen atom. So 4 in total. Yes, we have O2. And now we already have the production of OH-. We have to balance the charges. We have 4 negative charges on the left. How many will be needed on the right? 4 again. And now we have to balance the number of atoms. We have 2. Here we have 4O and 4H. So here we can balance that with water because we have the humidity in the atmosphere or directly water. So we have now 4H, we have 2 and 2, 4O. Everything is fine. But now when we create the overall redox reaction, we see 2 electrons here, 4 here. Well, what's to do? We have to multiply by 2 the part of the oxidation. And then we can sum up. We have 2 iron from the oxidation. And then we have 1 O2. The electrons are crossed out because we have 4 and 4 when we double that. But 2 water are remaining. And it leads to 2 iron 2 plus 4 OH minus. And now, well, when we have this in an aquatic environment, it is not very high soluble. There is what we call a precipitation of the solid iron hydroxide, and this is brown. That is the iron hydroxide. We have 2 of them. And this is precipitation, or you see it on the top of the iron, what we have outside, the brown particles. That's brown, the iron 2 hydroxide. That's the iron 2 hydroxide. Because we know already we have even an iron 3 plus possible, but the further oxidation from iron 2 plus to iron 3 plus needs more reduction potential. If you remember the table of redox potentials we were talking about, it was easy to bring iron in contact with or to bring iron in contact with copper 2 plus, and the copper takes the electron from the iron, but only up to iron 2 plus. Because the step to the iron 3 plus needs more power from the reduction potential from the other part. But in nature, of course, outside in the environment, we have a lot of different molecules. This could happen, the further oxidation. The further oxidation of these iron 2 plus hydroxide or iron 2 hydroxide when we have additional oxygen, it can be transformed into a mixed oxide or an oxide of iron 3, not a mixed one, sorry. And we have the iron OH. And water is created. And this is the iron 3 oxide, because now we have here, we have -2 and +1. Remaining is 1 negative charge from the hydroxide. And we have -2. So in total, we have to equalize 3 negative charges. So the iron in here has +3. And it comes from the oxygen. The oxygen here, 1 is oxidized to form the -2 here. Is reduced to, sorry, to take up 2 electrons from 2 of them here. So in total, we have even 2 of them here. Are you able to follow me to see the reduction in the oxidation? Yeah? That is half of O2. Only half of it. Yeah? That one is reduced Here 2 electrons. To these O, nothing happens because it's -2, it's -2, and it's -2 even here. So no change. But the 2 electrons needed for the oxidation, for the reduction here, coming from 2 iron. Each of these iron 2 plus delivers 1 electron and forms iron 3 plus. Okay? Yes, no. And that's the iron 3 hydroxide. Iron 3, and it's an oxide hydroxide. Because it's an oxide and a hydroxide.
Would the two iron atoms, which is on the product side, would they be split into +2 and +3? Because I can't follow the oxidation numbers. Because I know that there's currently 6 to be dished out of the oxidation numbers, and we've got 7, I think, including in the hot oxide. Do you know what I mean? We've got +1 on hydrogen, and we've got 2 lots of
Yeah, we have +1 here.
Yeah.
We have -2 here.
Yeah, so we've got.
So we have a -1 remaining.
Yeah.
We have -2 here. So in total we have -3.
Oh, okay. Sorry, I thought the 2 was multiplied, and the 2 on the left was
No,
multiplied.
so we have -3, but and we just have 2
Okay, right.
of that. When I have the 2 here, then we have 2 of the iron atoms in the molecule. If we have 2 in front, the overall molecules is just double.
Why not heavy group on the product side?
Why?
Why not heavy group of the?
That is the next step.
Oh.
So is one of the next steps. So this is a mixture of different iron oxides at the end with different hydrate and water content. Because this one now, the 2 of that, the 2 iron oxide hydroxide, they can be transformed in that what you're talking about in these Fe2O3 times water, crystal water, which is related to that. And this is now what we call rust, or the red brown rust. We have 2 iron, we have 3, 4O, 4, and we have 2 hydrogen. That is just a rearrangement of the atoms in this molecule. That's the first, which is big, and then it's forming the iron 2O3 with a crystal water in the surrounding. So this is a mixture of different iron oxides with different hydrate water content. And last but not least, sometimes when we have really quite a lot of oxygen available, these iron hydroxide, we had it at the beginning, even can form another molecule. So FeOH, the iron 2 oxide, can convert into a mixed oxide, which is the iron 3O4 times 2 water. Therefore, we need 6 of them. We have 2 of them, and we have to add oxygen and additionally for water. Well, first of all, let's check. We have 6 iron on the left. We have 2 times 3, 6. We have 2 times 4 is 8, plus 2 is 10, plus 4 is 14 oxygen. We have 2 times 0 times 6 is 12, plus 2 is 14. We have 2 times 6, 12 hydrogen, and we have 4 plus 8 is 12. So it fits. And this is a mixed oxide. This has a green color, that's green. And now please tell me what's the oxidation number of iron in this oxide, PO4. Sorry? Loud? The oxidation number of the iron is here. Plus 2. Now, 4 times minus 2 is minus 8.
Yeah,
Sorry? 8 by 3. Yeah, but that is not what's possible. Only an electron can't be split. So 8 by 3, it's not an integer number, so it could work.
Has to be
Sorry?
has to be minus 2.
Minus 2. Plus 2 times 6 times 3, 6. Doesn't work. We need 8.
Will it be plus 3?
Times 3, then 3 times 3 is 9. We have only 8.
The amount of FEs you have. So one with 2 FE would have positive 2.
2 of them positive 2 is 4 plus 3 is 7. The other way around. So 2 of them have plus 3, and 1 has plus 2. It's a mixed oxide. This is a mixed oxide because we have Fe with 2 of them with plus 3, and we have an Fe with plus 2, and then O4. When you calculate, 2 times 3 is 6, plus 2 is 8, plus 8. And here we have minus 8, so that works. And this is what we call a mixed oxide. From time to time, we find that. And we can't split the electron, so only partial charges don't exist. But what could happen is we have one with the plus 2 and 2 of them with the plus 3 oxidation. All of these in parallel happens, and last but not least, 2 of those, 2 of the Fe3 or 4 times water can be transformed into black iron oxide, Fe3O4, plus water. When it is drying, then we have here a black version of the iron oxide, the pure iron oxide Fe3O4 without crystal. With crystal water, it's green. Without crystal water, it is black. Yeah, two H2O. Then we have here 4. Okay. So the oxidation is quite complex. So we have different oxidation numbers of the iron. What we mainly see is this red-brown. Where is it? The red-brown rust. Here, the iron 2 oxide, Fe2O3. But it starts to build the brown hydroxide, then the iron 3 oxide hydroxide transformed into the iron 3 oxide, and this can be further oxidized to form the green or black mixed iron oxide. As complicated like this, normally you won't have it, but of course all the metals can corrode. And this is an oxidation. Of course, in each single case, you have to figure out what are the reactions, but mainly oxygen is available, even water, which enhances the conductivity. If you have a direct contact with water on the metal, you have a high conductivity because water has a high conductivity, so electrons and other charges like hydroxide ions or protons can move quite quick when you have directly water in the environment. That means the corrosion process can be from the speed can be enhanced when it's very humid or directly wet. So that's always a problem in engineering topics. We think about how to protect the metals from corrosions. Do you know any idea, or do you have any idea how to protect a metal from corrosion? Galvanization, yeah, others?
Could you, for example, put a layer of aluminum over it?
A layer, yeah, this works because then you have the aluminum oxide covering, coating. So different colors coating. That is, again, it must be quite dense. That there is no way of oxidizing agents directly to the metal. How?
You can put a more reactive metal on the surface of the less reactive metal. Obviously,
yes, it's a good idea. We call it offering another one. Offering another not so expensive and good available metal, putting into contact with the other, which should be protected, and those which has the redox potential more on the negative side will be oxidized before, or spending even electrons to protect the other one. Controlling the temperature conditions. Yeah, directly, what should help the temperature? Again? A dry condition, yeah, very dry, yeah, that helps, yeah. Other ideas? Instead of having an offering metal, you can directly connect it to the electrical power grid, and hand over electrons from the electrical power in the direction that an oxidation will not happen. Because at the end, it's a transfer of electrons. And if you give electrons from another electrical power, again, the direction of oxidation, it won't happen. So there are different ideas of corrosion prevention.
If you suppose ask the question, write down the reactions for iron corrosion, do I have to write 1, 2, 3 separately, or just the main one, which is the red brown?
Well, I think the main one helps if you know even the first step, the filling of the hydroxide, and then go to the main one, right? And you don't have to know the intermediate one here. You can come from the hydroxide directly to the rust. Because here this is just an intermediate and rearranging to that red-brown rust.
When the chemical color to the plant should be of the dendrite reaction condition.
You must speak very loud to me.
The chemical compositions, the color to paint the sheet to prevent pollution.
Yeah.
But the chemical composition.
The chemical composition of these salts, yeah? Yeah, we will talk about these different topics, corrosion protection now. There is even one student from, I think he's from industrial engineering, and now he is doing his bachelor thesis at Hutz Diesel. Hutz is a company, they are producing diesel engines in Ruhsdorf. It's half an hour by car from here, very big company. And this student has a contract there, he's doing his bachelor thesis at Hutz, and they think about corrosion of metals. And he's doing his bachelor thesis now. And the idea is to use different biological systems for corrosion protection, because even in biology, a lot of processes in our body and even nature outside, at the end, it's a kind of transfer of electrons. And here there are already products existing on the market on biological systems, and his job is to figure out what's existing and what helps really for their application to protect from corrosion. So, well, one idea is covering the iron with a less noble metal. And what is a less mobile compared to iron? If you try to think about it. Aluminium, yeah. Another one, zinc. And that is what is really, what we are doing is we coat the iron with zinc. So here, for example, zinc. So then we have here our, let's say that's the metal plate here out of iron. And this one is coated with zinc. And the zinc then is oxidized, forming zinc 2 plus 2 electrons, and the 2 electrons always are available to stop the oxidation of iron. When the zinc is gone, of course, then iron starts to be oxidized. The ships, when we have talked about the ships, then they are coated with a color, with an organic layer. With an organic layer. If you have organics, a lot of them are hydrophobic. So they are not really willing to be in contact with water. So they are hydrophobic. They try to not to let water on it.
Why not use oil?
Yeah, if I use oil, that is what my father did, but I was not happy about it, because you can coat the what's the sound in the English, when you have a house around the house, the fence, metal fences, no oil. But by rain, and after a while, the oil is washed away, and then you have the oil in the garden, in the soil, and that is poison. Fauna and flora. So here it's not a good idea. You need a covering which is stable on the metal, and therefore organic coatings are used, which are hydrophobic. And of course, it's similar to the zinc, but this is not an oxidation of the zinc. It's just keeping sure that there is no contact to the environment.
But use it in a closed system.
The oil, you can use it, yes. Of course, that is used, for example, in the engine industry. Sometimes in a closed system, you're totally right. They spray an oil on it, a very thin layer, and then they wash it after when they need it, because they have to store it for a while, and in this while they could start the corrosion. Then they spray a thin film of oil on the metals, and before they build the engine, they can wash it once more and reuse the oil. That's a good idea, but outside line. So that is similar. Yeah, here you have the iron, and you coat it totally. In this case, the function is we have a dense coating. This is not oxidized and not reduced. It's just keeping sure that there is no direct contact with the environment. And the organics, of course, doesn't deliver electrons to the iron, and even not take electrons from the air. What you were talking about with the aluminium, that is an industrial process, and it's called passivation. That's typical, using an aluminium on the surface of the iron, building this oxide. That's a dense layer protecting the aluminium, but even, of course, in this case, iron below, and that's called passivation. Another one is here. This one is even what we call an offering material. Yeah, the zinc, for example, that's the offering material. And this can be done as a kind of offering electrode when we do it actively. We just have a contact. We even don't have to coat it totally, the iron. We just keep sure that there is an electrical contact with, for example, zinc electrode. And that's just an electrical contact. Because at the end, it's just important that the electrons come from the zinc to save iron from oxidation. So this can be done by zinc, offering electrode, or even an electrical current. Instead of an electrode, electrical current. Can be used. Well, then we have again our iron here. And now we just have a contact to an electrical circle delivering electrons. So electrons are here delivered to the iron to save the iron from oxidation. So a cathode in an electrical DC power source. So we see, again, the main point of chemistry is always the transfer of electrons, and here we can see directly redox reactions.
First one, third process, do you constantly have to supply electricity?
Constantly a very low amount of power. Otherwise, it's done.
Does it be like particle?
Excuse me?
What does it be like a particle?
Yeah, you have to think about that. This is not really much power, which is very, very low voltage and current. So you have to transform it from the normal power source from 230 volt and 50 hertz to a small amount of that continuous. Small amount of power is quite a little bit. So that is not a big point. If you have an expensive application, that doesn't play a role. It's much more to replace the whole system after a while costs much more than continuously very low power use. Yeah, it's called cathodic protection. Yeah. Yeah, that's where, for example, that is used. Yeah. So in the railway, did you hear it? So here you have the lights, the train is on, and these are made out of iron. And in this case, they're connected. You see, from time to time, there is an electrical cable connected to these iron lines where the train is on, delivering very low amount. Even you can touch it, there is not a problem, but it's protecting mainly from corrosion. Sorry.
The base electrons, I think it's a neutral connection. Because there is so they have to wire like one, and the train is passed connected to the neutral side. So which is the difference.
Yeah, so there is a potential difference, and then it's going down. Okay. Any questions? If not, then we are done with metals. The main things I'd like to share with you. This was here the topic, corrosion protection.
We discussed what redox
Discuss one redox equation for that.
it's good methods. The chromium and iron stuff.
Uh-huh.
I'm trying to follow the
Maybe you can come in front and write down what you find, and then we try to figure out the right way.
So there was a chromium 3 plus and an Fe2 plus cell. And I was trying to figure out what's getting oxidized, what's getting reduced. So chromium, as we know, we have chromium 3 plus. The reduction potential, the reduction equation kind of looks like this.
You just have to check that the online students can participate. 1 second. It's always difficult to figure out how it works. What did I do before? Now it doesn't work. 1 second.
Or we can do it over there on the.
Okay, now it should work.
Yeah, but it's
Yeah. Online they can see it, I think. Yeah? Okay.
okay. So the reduction potential of chromium kind of looks like this, and where the reduction potential of chromium is negative 0.74. And if you have iron,
Please add the unit volt.
okay, yeah.
Always think about the unit in the exam. You will have a reduction of points if you don't take the units.
And it is 0.44 negative. Now my question is, I want to ask,
No, it's a 0.34. I was.
that
I just remember it because we had it, I think, in our, or maybe I'm wrong. Sorry, maybe just look it up. What did we have in our Linux potential? Table for iron. No, for one. Yeah, you might have a different source. I had for one, you have for four. It's fine. Could be a little different for different sources.
Yeah. What I wanted to ask is like, which one of them is getting oxidized? I believe it's the chromium, but from what I saw online, people are saying it's iron. I don't know why. Because the reduction potential for iron is technically greater. I think chromium should be the one getting oxidized. Yeah. So
But if you think about in chromium, you have even different oxidation numbers.
no, I don't know.
But here we're talking about
I'm only talking about this oxidation state and this oxidation state. This is the only one that I'm referring to. And like, if we look purely at the values, which one should be the one getting oxidized? This guy here. It should be the one getting oxidized. So like, can we solve this together?
right?
Yeah. So what I did was, I know that I have to multiply this guy by 3 and this guy by 2 if I want 6 electrons on both sides. So I'll get 2 Cr3 plus 6 electrons and 2 Cr. And here I'll get 3 Fe2 plus 2 electrons and the Fe. 6 electrons. Oh yeah, 6 electrons. Thank you. Okay, so if this guy gets oxidized, it wouldn't move in this direction. It would instead move in the opposite direction. Yeah. I mean, sorry, it would.
Wrong way around it.
I would be reduction. It's not supposed to be getting reduced. If this guy is getting oxidized, it should go from right to left. Yeah. So it should go 2 Cr to 2 Cr3 plus plus 6 electrons.
Yeah.
What I want to ask is though, when we change the direction, do we also change the value from negative to positive?
Yes, this is of course the other way around, but here in this way, this is okay because you have you have to write it in the same way to figure out which one is more easily oxidized or reduced.
So we need to write the overall equation.
So you have to write the overall equation, and that's all. The difference, of course, of the redox potential is only 0.3.
0.3. So will it be negative 0.3 or positive?
No, it's that you always can just measure it. And it works in the direction as you look at it now when you can summarize it. When you summarize it now we have 2 chromium plus 3
Plus.
Fe plus or 2 plus. And it leads to 2 chromium
3 plus.
plus 3 Fe. That is the way how it works.
Now, how would we write down the cell potential equation?
The cell potential is the difference, the delta of those two. Right? The delta E is exactly 0.30 watt. It is the absolute delta, the absolute value, the difference of those two.
Because Professor, when I tried to solve this online, I was getting 0.3 as well, the same as you did, but everywhere that I searched, the answer was negative 0.3 and not 0.3
Because
itself.
the potential is this, you are right negative because it works in that direction of the method.
That's why we
That's we have a negative value because the absolute difference is 0.3. In this direction, it's minus. In this direction, it will be positive.
Oh, okay.
Because this is how it works. And if you want to have it in the opposite direction, you have to invest exactly this value. Thank you.
So we will change the sign when we convert the equation. But that will be only in the final case, right? Before that, we cannot change the sign.
No, you can, of course, if you want to push it in the opposite direction, you have to add power. You can do that by electrical power. That is what we discussed when we talked about batteries.
So it will be plus 0.74 if we write something plus, right?
Yeah.
If we had the FP equation, if we convert it, then that will be plus 0.7.
It is when you have 0, nothing happens. And when you have plus 0.74, you push it in the opposite direction. So this is the direction how it works. Here we have a negative. When you want to have it in the opposite, you have to invest. And you can invest via coming the redox potential from another system or via electric power. Okay. Okay. Then I'd like to go on with another main topic, the short one. We already used some formulas in this field of chemistry, and we call it organic chemistry. And we'd like to talk about some single topics in this area. First of all, the new definition of organic chemistry is always when we have molecules containing carbon, hydrogen, and oxygen, mainly. But the thing is mainly carbon. So the definition is substances containing carbon, and so C, and very often hydrogen, oxygen, nitrogen, sulfur, the others, mostly in covalent bindings. Please remember the different types of covalent bindings. We have sp, sp2, sp3. sp3 is a sigma. sp and sp2 are pi bonds. Pi bonds is a double or then a triple bond. In sp2 we have double bonds. In sp we have triple. Think about it. So organic chemistry is chemistry of carbon. So the different types of bonding. Check it. I think it's chapter 3.2. We have single bond. This is sp3. Hybridization. And we have these tetrahedral surrounding around the carbon. Carbon in the middle of the tetrahedron. Then we have double bond. Here we talk about sp2 hybridization. We have a trigonal planar. Surrounding. Around the carbon. And last but not least, the triple bond. The sp type of hybridization. And that leads to a linear surrounding. Of the carbon.
Sir, what did you write after tetrahedral?
Surrounding. 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 Here we have the tetrahedral, the carbon in the middle, and we have here these 4 edges. When we talk about methane, it's an H, 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 and H, and this is the tetrahedron, with this triangle at the bottom, and here that's system. If we talk about sp3, sp2, we have a double bond, and we have, for example, the ethene molecule. And here we have the trigonal planar surrounding, and that's we have ethine. We have here a triple bond, and that's linear. Think about the types of orbitals, and you can explain exactly how the surrounding looks like in sp3, sp2, and sp. Sometimes we have even polar bonds. Sometimes only when we talk about different atoms. Here, for example, a very important one is the carbonyl function. Here, the oxygen has 6 electrons in the outer shell, because we are the 6th main group. We have 6 electrons, 1, 2, 3, 4, 5, 6 in the outer shell. That is what we always can check. 2, 4, 5, 6. The carbon, the maximum number of partners to be bound is 4. We are in the 4th main group, and maximum 4 electrons are available for sharing with others in form of a covalent bond. So we have 1, 2, 3, 4. The thing is, now the electronegativity of oxygen is bigger compared to that of carbon. We have to look the electronegativity here. It's called in German Elektronegativität. Here the data are coming from Allred and Rochow. But when we look it up, the green number here is 3.5 for oxygen, and for carbon it's 2.5. So here oxygen has a higher electronegativity, so the electrons will be more on the side of the oxygen. That leads to a partially charging the oxygen here, and the carbon is partially positive. So we have a dipole. Yeah, we know that already from the water molecule. In the water molecule, it's more extreme because the difference between oxygen and hydrogen has to be evaluated. And here the oxygen, of course, again has the negative partial charge. That is the carbonyl group. An important one, that here is the signal for a dipole. And now, well, these carbonyl group can be placed at different sites in an organic molecule. When it is at the end of an organic molecule, like we have it here, CH3, and at the end we have the C double bond O, that's our carbonyl function, and 1 hydrogen left. And we have 1, 2, 3, 4 bonds on the side of the carbon. The carbonyl function here is at the end because there is no further carbon on the other side. Do you know how these type of molecules are named? That's a special type, a class of molecules. So again, ethanol, no, This is not a ketone, aldehyde. An aldehyde, It's an aldehyde. If it is at the end, we call it an aldehyde. So here it's ethanol. Because it comes from ethane, but it's an aldehyde. Because this is at the end. And in this example, it's coming from ethane. Ethanol is the name. Always when we have an aldehyde, we call it al at the end. If the carbonyl function is not at the end, it can be somewhere in the middle of a long chain carbon molecule. Then we call it the ketone. And in the middle, the first of it, what is the molecule when you just talk about hydrocarbons? The smallest one, the smallest ketone we know. How many carbon atoms do we need? 3. And what's the name of a carbohydrate with 3 carbon atoms? Propane, and propanone is the name for the ketone. Propane is the pure hydrocarbon. So here that's an aldehyde, and when we have a molecule like this, C double bond O, and CH3 again. This one here we see our carbonyl function is in the middle. Then we call it a ketone. And in our example, it is propanol. This works only at 3 or more carbons. Otherwise, it cannot be or anywhere. So aldehydes and ketones. The formula here is C2H4O. Here we have C3H6O. And there is a special other molecule. So the carbonyl function is very important. Aldehydes, ketones, and there's even one other molecule where the carbonyl function is part of. It is the carbonic acids. So another one important is the carbonic acid. We already had an example, I think it is vinegar, acetic acid. And this is CH3. And then we have the carbonyl function at the end, but not a hydrogen. We have a hydroxide here instead of pure hydrogen atom. And this one, when we have here the carbonyl and the alcohol function at the end of a hydrocarbon molecule, this is a carbonic acid. And in this case here, it is acetic acid. And we write it here in another form, CH3 short, and the carbonyl function, and we have here an O and the proton. And this proton is the acidic one.
Don't we call it carboxylic acid?
Carbonic acid, we call it carbonic acid. Maybe even is called carboxylic acid. Carboxylic, how?
Carboxylic.
Carboxylic acid. Maybe you're right, not sure. Carboxylic. Maybe you have to, or we have to look it up. I thought it's only carbonic acid. Maybe you're right, but the acidic proton is this one. Why? Because this one can be delivered, and then we have the CH3, CO, and O. Only the proton is delivered, so the electron remains at the carboxylic acid. And then we have a negative charge here, plus a proton, which is decreasing the pH. We did some calculations in this example, if you remember. This is a weak acid. And we did these calculations, what's the pH of a weak acid, where we developed the formula. It's something like 4.7 something. Depending on, of course, even on the concentration. We had the pKs of 4.74. So this is very stable because we have a mesomeric other form. Here, another form exists, the BH3, and the pair of electrons here can switch over here, and then that one comes over here. That's the same molecule, but now the charge is here on the upper oxygen atom, and the double bond is here. This is very stable because we have two options for delocalizing the electron, the additional electron. It can move. That's very stable. And this one here is the acidic, we call it acidic proton. And that is delivered. Another one to be remembered is the different types of pure carbon. I have to look to the. So the different types of pure carbon, you remember sp3, pure. What is it? When we only have carbon and all of the carbon atoms on sp3 form, how do we call that material? Again? Diamond. That is a diamond. Please check it once more. And if we have pure sp2 types, what is the name of this? Graphite. So the same element, totally different behavior. Diamond and graphite, totally different. So, of course, you can create diamond out of graphite, but that needs a lot of energy, pressure, and then you can create a synthetic diamond.
I've searched this on net, and the carbonic acid has water on each side of the carbon.
The carbonic acid.
For example, instead of CH3, there will be OH alone.
So, yeah, that is the hydrocarbonic acid. Then you are right. It is, to write it down, it's salt carbon in water. It's called salt carbon dioxide in water. CO2 in water. CO2 in water. The formula is H2CO3. Isn't it? Yeah. That is salt carbon dioxide. That's carbonic acid. Yeah, you're right. You're right. Sorry about that. So the right name is carboxylic acid and not carbonic acid. Thank you for that hint. And cross it out. So here, diamond graphite. We talked about that. Yeah, in the diamond you have pure sp3 surrounding. In the graphite you have pure sp2, leading to polycyclic aromatic hydrocarbons, or here pure carbon, polycyclic carbon structure.